Leave the homotopy theory and model structures for next week and talk a bit about the tensor product. Okay, and I will begin by reminding you of the tensor product of operads. So there is a tensor product. I don't know. He must be confused. There is one important which is often called the Boltzmann-Vogt tensor product. And I will write it down for colored operads right away. For two operads, CP and PQ, tensor product, which I will just write P tensor Q as C cross D, the Cartesian product, a set of colors, and then the operations are generated by operations of two kinds. You can take an operation from P and pair it with any color in D, or you can take an operation of Q and pair it with any color of C. Okay, so P tensor D, which would lie in P tensor Q of C1D, CND, and lands in CD for any P in P of C1, C and C, and any D and D. And the other possibility is a symmetric one in P tensor Q of CD1, CDM, CD for any C in C and Q in Q, D1, DM, D. So you all know this in the uncolored case, because I have to put some relations, by the way. I will come to that in a second. But where the slogan that you should remember is that the P tensor Q algebra is a P algebra in the category of Q algebras, or vice versa. It's a symmetric tensor product. And there is a relation which I will draw pictorially, because otherwise I get confused. You could start with such an operation, P tensor D, so this takes input C1D up to CND, and then you could at each stage compose it with here C1 tensor Q up to CN tensor Q. So this one would go from C1 D1 up to C1 Dn, and Cn d1 up to Cn dm. Okay, I'm putting these labels for a reason, and you could try to do it the other way around. So you have CD, you could start with that operation Q, C tensor Q. This gets you into CD1, CDM, and then you could apply this operation P. So this is P tensor D1 up to P tensor Dm. So here it's C1 D1 up to Cn D1, and here you get C1 dm up to C Cn dm. Okay. So what I mean to say is that if you take P tensor D and you compose it with C1 tensor Q up to Cn tensor Q, you get the same as if you take C tensor Q and you compose it with P tensor D1 up to P tensor Dm. Okay? So that's a relation. So, yes, I'm going to emphasize this point. So, sorry? You take the operation P tensor D, and you compose it, you insert C1 tensor Q up to Cn tensor Q. But you see, and this is why I drew the pictures with all the labels, that the inputs are in the wrong order. So you have to apply a permutation for the suitable permutation. So, which you see by comparing this order to this order. Okay. So I'm emphasizing this because this tensor product only makes sense for symmetric operads. If you work with non-sigma operads, there is no tensor product. However, you will see that if either P or Q has unary operations only, there is no permutation involved. So in a non-symmetric case, you can tensor an operad, you can tensor a non-sigma operad with a category. Yeah? But you cannot tensor two non-symmetric operads, generally. Yes.
But it's just an ordinary Cartesian product.
That's the Cartesian product, yeah. And I will write a formula for dendroidal sets and simplicial sets which reflects exactly this point in a minute. So now we get to the tensor product on dendroidal sets. And it is completely determined by the fact that it is closed, or equivalently, i.e. preserves colimits in each variable separately. And on representables, omega s tensor omega t. Okay, this is going to be the nerve of omega s tensor omega t. So this is, just to emphasize, this is a monoidal structure. On these sets, and this is the Boardman-Vogt tensor product on operads. Oh. So some properties, some basic facts. For the diagram that I've drawn before, so maybe I'll write the functions again. You can view any simplicial set as a dendroidal set, and then if you take the tensor product of simplicial sets viewed as dendroidal sets, you get just the Cartesian product viewed as the dendroidals. Okay, that's the same remark as that the tensor product of two categories viewed as operads is the Cartesian product. And if you apply this adjoint to the nerve, so you use a dendroidal set to generate an operad, then tau of maybe some other letters, I don't know. U tensor V is tau U tensor tau V. So the operad generated by the tensor product of two dendroidal sets is the tensor product of the operads. Or in other words, the left adjoints that appear in the picture before are strictly monoidal. Well, this might be a bit too strict. But, So now, with these definitions, next week I will write down the theorem that dendroidal sets is a monoidal model category. So this tensor product has very good homotopy theoretic properties. Very much unlike the tensor product on operads or unlike the tensor product on the Lurie infinity-operads. Yeah? But to prove that, this definition won't help you very much. So I want to explain a little bit what this tensor product looks like on representables. Okay? So what does omega s tensor omega t, that's the thing which occurs there, look like? Now, if you know exactly what it is from this equation, and also from the remark which we made comparing categories and operads just a minute ago, you know exactly what this is for simplices. Yeah? So recall that in simplicial sets, delta n cross delta n, the product of two representables is of course not representable, but is a union of representables where the union is over the shuffles. Yeah? So I'm going to write down exactly the same is true here. Yeah? Exactly the same for trees. So I need to explain to you what is a shuffle of trees. Yeah? Provided you know what the shuffle of trees is. But I must say, well, I know how to do this, and I worked a lot with it, and it creates lots of combinatorial difficulties, but I do not know to what extent these things, I do not know much about it from a combinatorial point of view, and I do not know whether combinatorialists have studied this. For example, we of course know exactly how many shuffles there are for the simplices. But I have now, I can write some sort of inductive formula, but I do not have a nice closed formula for the number of shuffles of trees, for example. Yeah? And anyway, we'll see.
Well, there should exist genetic series for tree types. In non-commutative variables.
Yes, it would be nice to write some formulas.
Composition.
Yeah.
Something like that. Guess, just a guess.
Yes. So let's look at an example, okay? So, small example. Suppose this is S. And this is T. And I think when you see this first, it's handy to label the edges. So this is ABC, and maybe to distinguish, to emphasize this is a different type, let me label these by numbers. 1, 2, 3, 4, 5. Okay? And I also gave the vertices different colors. So on a piece of paper, this is a white tree and this is a black tree. And here this is the green tree and this is the white tree. I will still call them black and white. So S tends to T, short for omega S and omega T, is the union of representables and you start anything in the union of representables, right? So I haven't said anything. You start by putting, let's say by putting copies of S on top of T. Okay? So I'm going to write them all down for you. Maybe I'll write a sentence first. Starting by writing copies of S on top of T. And then circulating the black vertex, which is only one, and is only one in this case, the black vertex, down until you reach copies of T on top of S. That's easy enough to do in this example. Of course, the order is arbitrary. I could have started the other way. But what did I say? Copies of S on top of T. So I write T. 4, 5, and on here I put a copy of S. Okay, and to realize that this makes sense in this Borden-Folk tensor product, you should remember that the colors are pairs of colors. So this is now the color A1. Okay, then I can do this operation. Little a tensor this operation. So this gets me into A2, I will not write the parentheses, A2 and A3. And then I have another byte operation which gets me into 4, 5, A4, A5. Here I apply the byte operation which goes from A to BC, read in the other way. So I go B2, C2, B4, C4, A5, sorry, okay, B5, C5. So you see, the root of this tree is the pair root, and the leaves are exactly the Cartesian product of the leaves. So this is true for any sort of maximal shuffle. So n plus here for simplicities, n plus n is the maximal dimension. If you write a maximal shuffle, maximal dimension, whatever it means, then you will see that the Cartesian product of the leaves of these two trees is going to appear as the leaves. Okay? Now here I see two copies of the same vertex, this vertex. So I percolate that through this one. That's just language, of course, doesn't mean anything. So let me try to do that. I think it would have been clearer if I wouldn't have made them all binary. Let me repair D. I can still do that, I think. So B, C, D, B, C, D, B, C, D. This is C2, this is C4, this is C5. Okay? So I percolate this ternary vertex through this white, the two copies of this ternary vertex through the white vertex. So I get a picture like this. And now this one has to be multiplied by 3 somehow. This is the part of the difficulty in counting these shuffles. Okay? And you can check that this is well defined by just writing the colors. So let's do this. A1, nothing changed on this side. B2, C2, D2. This is the white vertex, A3. Now I have a black vertex, so I change the letters. B3, C3, B3. And now I'm going to from 3 to 4, 5. B4, B5, C4, C5, D4, D5. Okay? And again, I have 9 leaves, which is 3 times 3 is the Cartesian product of the leaves.
It's very close to the distributive law in the Poisson opera, you know. You put up and down the commutative product in the Lie bracket, and you already have the shuffles appearing.
Okay. There's only one more in this simple case. These are two copies of the same vertex, and I can percolate it through this one. So I get A1. B1, C1, B1, and then copies of T, I hope. So from B1 I go to B2 and B3, and so on. Yeah? So this is, sorry, now I lose my letters. This is S on top of T, and this is T on top of S. Now if you do this, it's a linear order, but if it's a bit misleading. If you do this for bigger examples, it will be a big partial order. Okay? And also, you should think a little bit about what happens if there are nullary vertices. Maybe it's a bit easier to think of pushing upward vertices instead of percolating. So let's read it from this side. I push this black vertex up through these 3, so this one goes down. And since this is binary, 2 of these appear. Now, if this had been nullary, none of these appear. Or if you read it as a percolation, you can percolate through a nullary vertex, and then suddenly these vertices can start appearing. Yeah? So, okay. Now, so it's a union. In this case, it's a union of 3 representables. How do you glue them together? So this is related to the Bournemouth.
But you keep all of them. They are not just one coming to the other. You say percolation. You keep the intermediate steps.
Yeah. Okay. I keep all of them. So this is a union of 3. If I didn't make a mistake, this is spontaneous but very small example. then this is a union of three representables, and we have to decide how we glue them together. So let's look what we did. So we percolated this one through this one here. So these edges, something happens to these edges. And these are the new edges that appeared. Now if you contract these two edges in this tree, or if you contract these three edges in this tree, you get almost the same tree. Now you get two isomorphic trees. So there will be a tree which I will try to draw. Six guys here. 1, 2, 3, 4, 5, 6. Let's for example order them like this: E2, C2, D2, B4, C4, D4, B5, C5, D5. So there is the way I've drawn them, there is a planar map here, which is a composition of two interfaces, given by contracting these two. And here you see that these, I hope, that these leaves appear in the wrong order. So there is also a map here, which is not quite a composition of three interfaces, but it's a composition of three interfaces and an isomorphism of trees. Okay? So maybe I'll write this for clarity. The compo of two interfaces, and here composition of three interfaces and an iso. So gluing these two together means taking a push out over this tree. Okay, and you can do something similar here. Maybe a piece of color chalk. So what happens here? I forgot. So I think if we contract these two, I hope we get the same as contracting these three. Is that correct? Yeah? So there will be another tree. 1, 2, 3, 4, 5, 6. 1, 2. Okay, so this is by contracting the red. Here,
Does it make any difference whether the vertex becomes white or black?
Well, if you contract a white and a black vertex, it doesn't have the color black or white anymore. Okay, it's a gray vertex or something. So I like the better. Okay. So if you
Excuse me.
yes.
One way to think about the ordinary shuffle is by looking at ordered points, some subset of the hypertree. You look at points strictly ordered.
Yeah.
And you take the product and you decompose. So if you take trees, you can think about partially ordered sets of points and take the product and decompose it. Is this something different from this, or is it the same thing?
I don't know. It's a little more than just partially ordered because.
Well, I mean, you have an inequality for every branch.
Right, but you need to keep track of the arities. So if you start shuffling partial orders, then you probably have to put in some more information. So if you want to practice a little bit with these shuffles, which I'm sure you won't.
This is our homework for next week.
Right?
This is our homework for next week.
So I will write down a theorem. Which is crucial in the whole business. Let S and T be trees. Let E be an inner edge in T. And I'm going to write down something which may look strange to some of you, but will look very familiar to some others. I'm going to write down a subobject of omega s tensor omega t. And I'm going to tensor omega s to the inner horn. This is a union of faces, so it's a union of representables. And I told you the tensor product commutes with colimits in these variables separately, so you know exactly what this is. Yeah? And you can take delta omega s tensor omega t. So this is a push out over, if you want to write it really, well, I don't do that. Okay, it's a push out over delta omega s tensor under et. And this is.
The delta depends on E, or it's just the sum of the faces?
Oh?
The delta is delta E, or the sum of the faces, the delta here?
Lambda.
The E is in the
This is a delta. We
Okay.
agree on this, to begin with? Yeah.
So
So this is all the faces of
Okay.
S, and this is all the faces of T except one.
Okay.
Okay? So this is a composition, a finite composition of pushouts of inner horn inclusions. Lambda, let's say, let's write something, lambda AR into R. For suitable trees R. Now to write down a nice proof of this fact forces you to think a lot about the combinatorics of these shuffles and how exactly they're glued together and so on and so forth.
So does R range over all possible shuffles less than 2?
Sorry?
Does R here range over all the possible shuffles?
Right.
Less than 2?
Yes, but in the on the way you need other trees and yeah. The number of inner horns that you have to push out, which are involved, is not the same as the number of shuffles.
So what's that superscript? Is that E? Or is it E?
A, well, it's just any, okay?
Oh, I see.
Of inner horn inclusions.
Oh, of all horn. Okay, okay. Thank you.
For suitable trees R and inner edges A. So I will stop in a minute too. The head of department leaves, I have to be careful.
I've got a very unpleasant meeting.
When that cuts away, yes. See. So there is another way of writing this. Now maybe I can discuss one topic. So another way of writing this if X is an infinity-operad, then home omega s X to home delta omega s X is an inner vibration, inner configuration. Yeah?
Which harm is meant to?
Sorry?
Which harm?
This is the home. The home is the home corresponding to the tensor. Okay? So it's completely topological. It's literally the same. I mean, I'm not exaggerating here. It's literally the same thing. So you could ask yourself, if you have, so more generally, we conclude that if A to B is a map that can be obtained as a retract of a composition of push-outs of inclusions of the form delta omega s boundary inclusions, then home the restriction map on AX is an inner confederation so this, under the assumption for X and infinity-operads in the kind of complex. Okay, so it's just formal. Take the saturation of these boundary inclusions. Now, what is the saturation? So you know that if in simplicial sets, if you take boundaries of simplices and you close them off under these things, you get all the monomorphisms. Yeah? And it has to do with skeletal filtration of the simplicial set. Now here, it's not true that every dendroidal set has a nice skeletal filtration, and it's not true that you get all the monomorphisms. So the maps A to B that can be obtained in this way are called normal monomorphisms, not very imaginatively, but they're called like this in a sort of more general context. The work of Szynski. Normal monomorphisms, and they can be characterized as follows. These are exactly the monos, the ordinary monos, A to B, with one further property for which for any tree T, so that's an objective omega, automorphisms of the tree T acts freely on A of T. I wrote it as a subscript of AT. No, sorry. BT minus AT. Okay? So let's remind ourselves, A and B are pre-sheaves of omega. So for every tree T, I have a set BT, and I have a subset, or at least an injective map AT into BT. I take the complement of the image, and automorphism of the tree is the automorphism group of the tree T is going to act on all these sets because it's a pre-sheaf. Okay, and this action should be free. So if you think of cell complexes, you should obtain B from A by adding free cells, not of a dimension but of a shape of a tree. Yeah? So that sounds very much like equivariant topology, equivariant GCW complex, essentially, if you're familiar with those. Okay? So maybe that's a good point to stop.